Archiving started.
Okay, want to welcome all you guys to the first talk of our physics space science series, and want to welcome our first speaker. This is Justin Brown, and he came all the way here from California, and he's an IRIS-sponsored speaker. He's going to talk a little bit about what that organization is and what it is they do. First, a little bit about our speaker. He has an undergraduate double major in physics and geosciences from the University of Wisconsin-Madison, and a master's degree and PhD in geophysics from Stanford University. And he's got postdoc experience at Caltech. And he says you're current an NSF postdoc at University of Miami, Ohio. And so what he's going to talk about today is about being a seismologist and careers in seismology. And also, I just want to let you guys know there's a sign-in sheet that's floating around, and there are also some other handouts having to do with IRIS and what the organization is. It'll be there. For the undergraduates, like we said last week, there'll be a report due next week. I'm glad a lot of you guys were able to come despite the weather. So, yeah, good job there. So I'll turn over to our speaker.
Thanks, Dr. Garrison. So, first of all, I'm glad to be here. Thanks for having me. As Dr. Garrison pointed out, today I'm going to discuss a lot of things related to the geosciences and how people who have backgrounds in physics and mathematics and engineering can easily transfer those skills into careers in the geosciences, specifically seismology. So I want to start with this cartoon here. It's a Calvin and Hobbes cartoon, and I don't know if you can read it, but I will read it for you. Calvin's dad is saying, hey, let's start at the beginning. When you add something, you increase what you have, you combine. So he's talking to his son about how to do math, basically. He doesn't want to learn this math. It's completely irrelevant to his life. His dad says, it isn't irrelevant. Everyone needs to know this. Calvin is upset. He says, I don't need to know. He said, I can't get along without math. So the dad continues to say, really, what do you want to be when you grow up then? Every job requires math. I think everybody in this room knows that. Calvin continues to say that's not true. I'll be a geologist. He, for some reason, is under the impression that geologists don't use math, and the dad concludes this cartoon by saying that's not really a job. So, on the contrary, I guess I'm here today to convince you that geologists and geoscientists, actually, we do have jobs, and they do use a lot of the skills that you garner as physicists. Okay, so as a geophysicist, in case you aren't as familiar with the field, it's basically the field of measuring, examining, modeling, and exploring physical properties of the Earth and its interior, planetary objects, from the depths of the core of the Earth all the way up through the atmosphere to space and beyond. And geologists are not always just spending time outside. So I was requested by IRIS, which stands for Incorporated Research Institutions in Seismology. They said, please show some photos of what you do as a seismologist. And so this is me in the field. This is near Death Valley, California. Yeah, sometimes we go outside. This is in Alaska. This is a seismic station near the Katmai National Volcanic Field. And most of the time, and I think those of you who are research scientists, you're aware that we spend most of our time sitting behind a computer playing with signals. So my specialty as a seismologist, which deals with basically the study of earthquakes and the waves that propagate throughout the Earth. There are other types of geophysicists, such as geodesists. Those individuals study the Earth's shape, its gravity field, and rotation. You have marine geophysicists, petroleum geophysicists. I'm sure a lot of you here in Houston are probably familiar with the petroleum field, more than even I may be. Mining geophysicists, so that's exactly what it sounds like. people who study the environment. There's many people in geophysics that are actually looking at water quality. And then exploration geophysicists, which is, again, things related to the petroleum industry and natural resources. The data that's used is seismic data, the wiggles that you might see in the movies. The wiggles are no longer on these drums, these big drums that you may see in the movies that basically record seismic waves. They're actually online. And part of what IRIS does is provide that data accessibility so that you can download it online and then use it in MATLAB or any of the other software tools that you might be interested in using. Electrical resistivity. We all know about that from physics. Electromagnetics, that's physics. People use GPS, gravity, infrasound, magnetics, and passive seismic data. All of these things are, you have a background, basically, and at least half of these pieces of data that are used for geophysics. If you're wondering about what's basically the employment sector of recent masters and PhDs in the geosciences, it's actually pretty good. The percentage of people in academia with master's degrees is, of course, going to be lower, but than those with PhDs who end up being professors or postdocs or research scientists. But there's also opportunities in government, and there's also a lot of opportunities in the private sector, and even not so much, but there is still opportunities to work in nonprofit as well. Money, something that everybody likes to care about. So well-paying career options with or without a PhD. I'm comparing a physicist to a geologist. A physicist who has their PhD, this is the 2010 median is a good six-figure number, around $105,000. The job outlook is increased 4% expected to increase by 14% by 2020. Geologists who have a bachelor's degree or an MS degree, their median is lower. However, this is not the PhD level, and it's around $82,500. And the reason for many people getting master's degrees, or if you have a master's degree and you go into the geosciences, the reason for this is that there's a lot of opportunity in the private sector, especially in a place like Houston, where the oil industry is very, very booming. You could compare this to an electrical engineer with a bachelor's degree. They make just roughly a little bit more. Civil engineers, a little bit less. But the whole idea, the big idea here is that geologists we're not broke. Geophysicists, same thing, not broke. You can definitely climb up the ladder, and by the time you are, into maybe a PhD and you happen to climb up the ladder in your company, you can make a lot more money. So this is the mean annual salaries of geoscience professions. What you can see on the right is the color coding of what types of geoscience-related occupations people have. So that's managers, engineers, people who are just scientists who work in labs. As you can see, everything has been very, 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 it's a growing field in terms of mean annual salaries. So as you can see, we get into this six-figure range when you get into the natural science managers, those people who have those management positions. Okay, so a little bit about what I do. I'm an earthquake seismologist, and what I focus on is understanding why seismic plates around the world give rise to these large, devastating earthquakes. What you're looking at here is basically our globe. The yellow dots represent earthquakes, and each of these yellow dots actually do a really good job of outlining the different tectonic plates that we have on the planet. As you can see, by far the largest of all of these tectonic plates is the Pacific plate, which is right in the middle. The Pacific plate is basically the plate that has caused, at one of these plate boundaries and one of these edges, most of the devastating earthquakes that we've had in historical times. That includes the Japan earthquake a couple years ago. Now, each of these plates moves. And when they move in different directions, and these different directions give rise to the different types of earthquakes that you can have. So as you can see, this Pacific plate, again, has these big, big vector motions that are going to what looks like the north and west. And as you can see, there is a very, very, very large vector located here, and that is pointed right at Japan. So Japan is the most seismically active archipelago, island chain nation in the world, and has most of the seismic energy is being released actually just from the individual earthquakes that can be as large as magnitude 9 globally. Some things that we also do as seismologists, as earthquake seismologists, is that we focus on helping the public when these bad things happen. So a really, really interesting year for us as seismologists, and it was a very busy one, was 2010. And it was a year of basically seismic hazard wake-up calls. First one being the Haiti earthquake, which occurred in 2010, in January 2010, and the Chile earthquake, which is magnitude 8.8 in February. The reason I like to compare these two, despite their different sizes, so the Haiti earthquake is a magnitude 7 earthquake, and the epicenter of this earthquake is located where the red is. The red corresponds to the strongest ground motion, and green is lighter ground motion. So you have an earthquake that occurs here, so you could probably guess that wherever you have your earthquake, you probably have the strongest ground motion. The intensity scale is not a measure of earthquake magnitude. These intensity scales are actually, again, have to do with how strong the ground actually moves in that individual plate. You can take an earthquake like like the Haiti event, and we found out that basically, first of all, 230,000 people were killed, 1.5 million went homeless, and this was the largest U.S. urban food campaign in history. We work with basically all of these different agencies that collect information like how many people are homeless, how many people were killed, and how to get aid to the right people. So as you probably remember from this devastating event, this is basically what Port-au-Prince looked like. In May, I was in Port-au-Prince, and it doesn't look anywhere near as bad as it did back in 2010. However, they're still in crisis. There are still people who are living homelessly, and this is also the poorest nation in the Western Hemisphere. So our work is very immediate whenever these devastating things occur. Okay, now I'm going to compare that earthquake to the Chile earthquake, which happened just about a month later. So again, the colors correspond to strong ground motion. The epicenter of this earthquake is here. This earthquake is basically 200 times stronger than the Haiti event. However, what we know is that if you take 400 Chileans and you put them in a box and you shake them at the same intensity as you would do for 400 Haitians, 399 Chileans come out alive. No one comes out of the Haiti box. So what are the reasons for this? Does anyone probably want to guess? I want to basically, you see what the intensities here of the strong ground motion are. This event is a lot of orange, as you can see. The Haiti event has a very focused area of red. Does anyone want to guess why the smaller earthquake has stronger ground motion intensities? Yeah. We'll go back to this one. Ground vibration. Did it also have to do with the infrastructure of the country? Yes, that's one reason. That's right. Resonating frequencies. Absolutely, yes. That goes with it. So that works with the earthquake engineers. That's actually a field, earthquake engineering. Any other guesses? Aftershocks are not being captured in what the total number of fatalities and whatnot are. The depth of the quake. The depth, yes. Okay. So the depth of this earthquake in Chile was much, much, much deeper. I'm trying to make sure I have it, 35 kilometers depth. And it occurred here, even though it's on the coast, it occurred at in a place where the sediments that are on top of here also are not particularly thick. If you have sediments that are really, 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 really thick, like we do in Los Angeles, and you can imagine if an earthquake occurs, it's like taking a sandbox and shaking it. Haiti. The depth of this earthquake is 13 kilometers depth. And this place is really fitting. The reason that it's darker here is that because, one, the depth of the earthquake, as you pointed out, is much more shallow. And then the second reason is because this is like Los Angeles Basin, it's really like one big sandbox, and you're just pretty much shaking it. Okay, so the epicenter was also very far from the capital city. 521 people were killed in the Chile earthquake. The ground shook for over 3 minutes, and there was a tsunami that was generated that is about 1.3 meters high. Okay, so then 2011 was the next year of busy seismology work. So the March 11th magnitude 9 earthquake in Tohoku, Japan, which I think everyone is familiar with, which created a very large tsunami and also other problems with the infrastructure of the power plant. And then a very, very strange earthquake occurred in the summer of 2011 in Mineral, Virginia, and that's what is being shown here. We don't usually think of Virginia as being a place that has earthquakes of this size, but it did occur. Any ideas why there was an earthquake of magnitude 5.7 in Virginia, just outside of D.C.? Mm-hmm.
Not because of the mining and the current extraction method. Is that a possibility?
That was one idea, and that doesn't seem to be the case, that it had anything to do with fracking, so no. Okay, so, no, there's no volcanoes around here, but that's kind of close. The interesting thing about the East Coast is that it's the oldest, the Appalachians are the oldest mountain chain that we have in the United States. And it's really all one big old fault. And every now and then, these old faults will actually rupture. So there used to be earthquakes in Virginia all the time because what was going on tectonically is that a piece of Africa about 1.5 billion years ago kept smashing into the east coast of the United States. And then a piece of Africa broke off and you get Florida. So those are just old faults. And then this one happened to rupture, and it could rupture again, and there were definitely more aftershocks that occurred in this event as well. Okay, so just to go into some things related to math. So as Calvin said that he doesn't need math, but he can be a geophysicist, he's wrong. Matrix algebra is king. Ordinary differential equations and partial differential equations, very, very key. In fact, we use matrix algebra in ODEs and PDEs to solve where we locate an earthquake comes from. Complex calculus and vector analysis, the people who are in geodesy, they tend to do a lot of that. You can imagine that vector analysis is really big, especially when you want to get precise plate motions relative to all the other plates. So that is very, very, very important. Statistics. Why do you think earthquake seismologists use statistics? It's the question that I always get every time I tell people I'm an earthquake seismologist. Yeah, exactly. When's the next big one going to happen? That's a probability and statistics problem. That's it. And then computational physics as well. So folks who like to model basically the dynamics of rupture, they use a lot of computational physics because it involves actually using all of these mathematical methods, but you need to do them on a really, really sophisticated supercomputer and to do it fast. You can imagine that, especially when you're looking at hazards, people who are studying tsunamis or looking at basically rupture dynamics that have to do with the fault, where does the fault slip? Faults don't just slip at one point, they slip over a plane. That's a huge computational problem to do quite fast. So if you want to explore geophysics further, I strongly encourage you to find any local geoscience talk anywhere. I'm sure NASA has some opportunities where they have talks and they bring in folks with geophysics backgrounds. One of the ways, actually, bringing up NASA, one of the ways that the plate motions actually get determined has to do with satellites. It's GPS satellites. And so a lot of collaboration occurs with the folks at NASA, not just at NASA, at JPL, but also all the other NASAs everywhere, all 12 of the major hubs. For those of you who are undergraduates, I strongly encourage you to get involved in an internship program, and that's what part of these pamphlets that have been handed out is about. So if you are a junior, and I'm not sure if it's true for seniors, but I know that if you're a junior and you're interested in the internship, please take advantage of that. And it pays handsomely, by the way. It's 10 weeks. They basically give you a crash course in New Mexico. You get to fly out to New Mexico. They give you a crash course in all the things you might need to know for your internship, and then they fly you somewhere where you're going to work with a professor or a research scientist in a lab or a government facility. They give you housing. They give you a stipend. It's a lot of fun. I did it when I was an undergraduate, had the time of my life, and it turned into getting into grad school. UNAVCO, they have research experiences for undergraduates in solid earth sciences as well. UNAVCO is more of the geodesy branch of IRIS. They work together. They're independent, but they do work together. So the seismologists, we run over to IRIS. The people who are looking at plate motions, they run over to UNAVCO. They all have money, and they all like to pay undergraduates for summer internships. Okay, so the details of, more of those details for each of those internships are listed here. Some of the things that I didn't mention is that you get to work with each other across wherever you are in the United States. So people in Alaska who are interns will work with and collaborate with people who are maybe in Maine or someone in California or wherever in the United States they are. The research projects also conclude in an all-expenses-paid trip to the American Geophysical Union meeting, which is in San Francisco every December. And it's expected that you take your research results that you have and you are able to actually present them. Many people have given talks, invited talks. Many undergraduates have been given that opportunity. And also people get the opportunity to sometimes even write up as the first author a scholarly paper. Okay, so it's pretty much the same thing with the UNAVCO-sponsored recess opportunity. All right, so with that said, I think I'm pretty much have nothing more to say. So, all right, does anybody have any questions? Yeah.
In your profession, what areas do you particularly focus on? Are you kind of a traveling geophysicist, or do you have a certain region that you perform?
I'm a traveling geophysicist. I specify in circumpacific subduction zones. So basically, I focus on Alaska, Cascadia, the San Andreas Fault, which is actually not a subduction zone, but that's okay, Mexico, and South America. So, and I've been to all of those places to actually do work. That's the fun thing about, I think, our profession is that there's always some place to go, and as long as there's money around, someone will fly you there somehow, and you'll live there for anywhere from a week to as long as even a couple of years. Yeah.
Quick question. I'm double majoring in geology and physics. Is that usually in industry accepted as highly as someone who did an active geophysics major? If they go to geophysics?
I did exactly what you did. I majored in geoscience and physics, double majored. And I was always told that that just gives you a leg up. That by no means, though, I know when I got to graduate school, some of the best people in my geophysics department there had never taken an earth science class at all, and they had a background in astrophysics. That was their major, and they turned it into 2 Nature papers within 3 years of starting in the earth sciences. I remember when she came to visit, and everybody, you know, what happens when you visit grad school, I think probably those of you who are grad students, and some of you can probably recall this, you know, the other students who are actually there before you get accepted, they all kind of scope you out. And everyone said, what's with this one person? She's never taken an earth science class. And I'm like, oh, she could probably figure it out. And she sure showed us up. So, yeah.
So when you say travel, I mean, I could see setting up stations or things like that, but what exactly do you do when you go someplace?
It's usually setting up stations. You set up stations and then service stations. Another thing is also there's usually a local institution, whether it be a government facility or if it is an actual institution like a school, and set up basically the online, making sure you can get all the seismic data to some sort of centralized facility where the seismic analyst that permanently lives there can basically get that data easily. That's most of what happens when we travel. Yeah.
You guys travel with teams or?
It's always in teams. There are occasionally times when people go alone. That's discouraged just because if something bad happens. Because we're going out into the middle of nowhere, usually. Either you're going out in the middle of nowhere or you're going to be somewhere in an urban setting where you're going to, it's usually a firehouse, a school, or a police station, or a hospital. Those are usually the places where we put seismic instruments in urban places. But then when we put them out in the middle of nowhere, you could be, you know, hiking for a while, and something bad might happen. So people usually, they give you the satellite phone, so on and so forth. That's not true in Alaska. An opportunity that I had with my IRIS internship was that I was with the United States Geological Survey, their volcano observatory, and I got to go and service a seismic station, and it was myself and my advisor. She and I both went out, and they would basically, what they didn't tell me I had to do, but what my advisor does do, is every year get gun certified, because in Alaska the wildlife is dangerous. So you can possibly get gun certification through the United States government. So. And she's short, and so that, you know, it's really, really funny. She was telling me how when she does her certification, they always have to adjust the barrel length of the rifle because she can't reach. So.
What was the death toll in Haiti again?
230,000. And 1.5 million homeless.
So how far along has earthquake prediction from the last 20 years anyway?
So the things with, we usually don't like to use the P word, because it can get you sued. So the thing that we use is the term forecasting, because the thing is that over the last 20 years or so, I think a better way to look at it is earthquake seismology is really a field that's really boomed in the last 100 years. It didn't really exist around 150 years ago. It was very, very primitive. But the things that we can do now, so for instance, the plate tectonics revolution didn't happen until the 1960s. So people didn't know that we had these big, huge plates that basically are responsible for very large earthquakes. So that was a huge move forward. The things that people can forecast, the things that we do a really good job of forecasting is we can pretty much pinpoint where we know earthquakes are going to occur for the plates. We pretty much know how big we expect them to be, so that's forecasting in itself. And we can also forecast the ground motions that are expected from all of these different parts of the world. The reason that I'm bringing that information up is because that's really where the bread and butter of earthquake forecasting is right now. The thing that we cannot forecast is the timing, but we can't forecast timing to the level that people want to hear. So if you take one part of the world, so let's say you take the Southern San Andreas Fault in California, and you want to look at the seismic cycle, or what the seismic cycle is to say, we know that there is a 30% chance that you will get a magnitude X earthquake at this place that will make these ground motions, and it's over the course of 100 years. Now, a lot of us won't be around in 100 years. So it can be frustrating for the public to hear those numbers about timing, because the timing thing, which is really a statistics problem, and it's really important for the insurance companies to know these numbers, so that if they build a building, they know what to expect. So the timing of earthquakes, that is still being improved, but the numbers are not ones that the public are particularly familiar with.
And in areas where you're talking about, I mean, what has changed structurally as far as the city mandating buildings?
Mm-hmm.
You know, now that we're smarter about this, how's that going?
That's a great question. So I'll give you the example of San Francisco. So the safest place to be in the city of San Francisco, it was found out back in 2006. There was a big, huge push to get like block by block information about the buildings, and it was presented at the 2006 Seismological Society of America meeting that the safest place to be in the city of San Francisco proper is in the financial district. The reason why is because those buildings, for the most part, were built after the whole field of earthquake engineering really exploded in the 1960s. So you have a lot of old buildings in San Francisco that have survived also those the 1906 earthquake. The buildings that sit on landfill, so basically someone took a lot of sand and they made the Marina District, and the airports, Oakland Airport and the San Francisco Airport, they sit on landfill. That's a problem. So that doesn't really have to do with the buildings themselves, but it really has to do with the land on which they sit. So that's kind of where things stand. So you can have a strong building, but if you put it on something that's really like you can shake it like a sandbox, that's a problem. If you put the building somewhere where you can actually get into the hard rock and really reinforce the building, then you're good to go. You're generally good to go.
I was reading something earlier, I think it was the abstract of the talk, that you were looking at kind of a low intensity signal from a slow slipping.
That's right. So that research, my dissertation. So a phenomenon that was discovered in 2002 is something that was originally coined nonvolcanic tremor. And what non-volcanic tremor is a long duration, low amplitude humming of a fault. And what's really enigmatic about this signal is that in some of the places that I just described, like Cascadia, you actually have a recurrence interval of when the slow-slipping non-volcanic tremor turns on. So for instance, it's pretty well known that every 13 to 14 or 15 months in the Seattle area of Washington State, this seismic signal turns on. And it's been shown, and this is most of my research has been, that you can precisely locate where the tremor comes from. The reason this is really important is because it's a seismic signal that represents slow movement of a fault that looks like you can forecast better than your ordinary magnitude 9 earthquake. So to this day, so there's a whole lot of nature and science papers on this. So to this day, we think that we can use this signal that would help to get at the timing of the big nasty earthquake that would happen. So you can imagine that if you have some sort of plate interface that slowly slips, it means that also at some point, the stressing regime of the entire fault should drastically change and result in a fast, big, large, devastating earthquake. So whenever the tremor turns on, for some reason, and I think this is a little bit premature for the news to do, but there's been a lot of articles and people saying there's going to be an earthquake because the tremor has been turned back on. And we're not saying that because we don't know that yet. And so that's part of what my research is focused on.
I know it's somewhat controversial, but there are those who claim that earthquakes are triggered by tidal, like when the moon's orbit is so that it's at perigee.
Yeah.
During a full tide. Do you ever see anything with signals correlating with lunar period?
Well, with non-volcanic tremor, yes, it has been shown that tremor can be modulated by the tides. That's been shown. That was shown very, very quickly. So basically, when it's high tide, that tends to be when tremor is on. It's only on during high tide, or it's strongest during high tide every 13 or 14 months. With regular earthquakes, this is where it gets controversial. And I'm not going to touch that.
Just one quick thing. That tremor, is it spectrally? Is it kind of a steady tone, or is it? It's
not harmonic. It tends to be between 1 and 8 hertz. Earthquakes that are of comparable amplitude, so magnitude 2 earthquakes, the corner frequency, or basically the frequency up to which a lot of the seismic energy is being released, tends to go up to something like 20 hertz.
Could you apply certain aspects of acoustical physics and that could study the way a frequency of a certain hertz travels through a certain medium?
Yes.
Like you said, it was built on a land, so it was a certain medium as opposed to a built on bedrock or something.
Yes. So there's a lot of people who used to be in medical imaging, medical physics, that go into seismic tomography. And so a lot of the seismic tomography that is done is when people do what's called active seismology. And I'm not involved in this. I'm in passive seismology, which is based mostly earthquakes. But the people who do active seismology, they basically set up a whole lot of sounding instruments, and then they make their own seismic source. So usually it involves, if you do this in water, you take an air gun and you shoot, and a wave will travel down to the ocean bottom, travel through the Earth's uppermost layers, and then be sounded on basically those sounding instruments, those sounding devices. And people who do this, and it basically tells you about what's the seismic speed, what's the attenuation of the subsurface. And so those are the tomographers, and it's essentially using basically ray theory. It's just ray theory. That's it. If you took optics, everything that you learned in optics is basically what active seismology is.
When you say attenuation, you mean such that like attenuate, could it be like an analog to like the attenuation of electromagnetic waves to different mediums?
That's exactly right. Yep. And a lot of the equations are the same.
So there's literally Snell's law.
You just always know Snell's law. That's just kind of the way it is. It's called, we call it the Snell parameter, and that's what people do a lot of imaging of, Snell parameters of the subsurface. And that's very commonly done, especially in industry for oil and gas. And they make a lot of money.
If I could ask, on the research that you did, I believe you said it's just your dissertation, has there been a lot more progress in that respect on that subject? In the time frame from when you did it to now, is there a lot more focus on it?
Yes. There are, I'll take an example of the American Geophysical Union meeting that was this past December. There was 2 full days just dedicated to it in the seismology section. So, yes. And it's become something that's common with science is that every now and then you're going to get a hot field and everyone jumps in. And then it kind of peters out. And then there's a new hot field. And so since this is 12 years old, it's starting to finally kind of see its peak. But most definitely when I was in graduate school, which was between 2006 and 2012, it was, I think one of the reasons that I ended up getting the postdoc that I have was mostly related to the fact that I just happened to be in the right place at the right time. I'm sure you can attest to this as well. It's the same in your field in physics, right? No. Okay.
You said you were using gravity as one of the things to look at. How are you measuring that? Is that using a satellite or are you taking a vacuum chamber yourself?
Not the vacuum chamber. So there's 2 ways. There's the archaic way, which you learn in applied geophysics, which is you basically take a gravimeter and you go outside or you go wherever you go and you basically plant something on a surface. You try to make sure that it's level, and you basically get a measurement in gals of what basically the gravitational force is at that point. And then you come back in another day and you want to see if the gravity changed at that exact same point. Now, that's the archaic way. There are satellites that actually do a lot of the monitoring of gravity, and that's where most of those folks get their data, the people who study gravity for geophysical purposes. One of the ways, the most applicable one that I can think of for people who are not doing industry-related geophysics that are interested in gravity has to do with climate change. So you can use these satellites to monitor the thickness, basically, of ice shelves. So in polar regions, to see basically what's going on. Is it really melting? Yes, it is. So.
I don't know what you asked. Is there any, we're taught, to assume that the gravitational field of the Earth is constant when we know it's not. With that question, is there any correlation between, say, anomalies in the gravitational field, if there are any, and tectonic activity and what have you? And could that also be a good indicator of potential, earthquakes and what have you?
Not to my knowledge, particularly with earthquakes, but with strong ground motion, absolutely. So the people who do strong ground motion, who are basically observational strong ground motion types, will convert seismograms that are in velocity and convert it to acceleration. And you can imagine that, when an earthquake occurs, that as the ground moves up and down, of course, the gravity field is changing. And so that's something that people like to do. So yeah. So that's a tectonic application of looking at gravity. Yeah. Yeah.
Any correlations with not gravity, but with magnitude? And any influence in the fact that, for instance, the North Magnetic Pole is going to move, and in a few years it's going to be in northern Russia. Any interaction between tectonics and magnetic poles?
Yeah. So in fact, the reason that one of the big, basically hitting the nail right on the head, plate tectonics was actually pretty much discovered using paleomagnetism. So people would take a device and they would cross the ocean and they would get these magnetic strips. They could tell that the ocean bottom, based on which orientation the magnetic field happened to be throughout history, and they know the age of the rock, but the minerals, the crystals basically aligned themselves with respect to the magnetic field at that time. So if you have a rock in one place that was basically set in the ocean bottom, at one point when the magnetic field is pointing in one direction, and then you just go like 5 miles away and it's pointing the other direction, and you know the age of both rocks, then that's one of the ways that they found out that, oh, these plates are moving, and that we know that from basically the reversals of the magnetic field throughout Earth's path. So that was kind of the big, discovery from doing that type of work.
Are the solar magnetic fields too far away to have any influence?
I don't think so. I think the primary one is just the Earth.
Any other questions? Let's thank our speaker.
Thanks for having me, guys.
And just a quick announcement, if you haven't had a chance to sign the sign-in sheet, it's up here. And also, I want to invite everyone back for next week. We're going to have Christopher John Kroll from Rice University here talking about ground dwarf stars.
Oh, that's cool.
Second.